Good morning, everyone. So let's get started here. I had you guys work on a lab that we hadn't quite gone over due on Wednesday. So we'll go over the stuff now. I just didn't want to make you guys have stuff due on Sunday of this week. So you will have some stuff due on Sunday at the end of spring break, though, April 4th. So make sure you keep an eye out for that. So let's talk about electrolytes and non-electrolytes. Thus far, we've been talking about solutions where one thing is dissolved in another. When we put ionic stuff or like metal, non-metal combinations into a liquid, they will dissolve and form what's known as an electrolyte solution. So a strong electrolyte solution would be something like sodium chloride. Each sodium and each chlorine are breaking apart into their ions. They dissociate. This dissociation allows for an electrical current to run through it. So if I had, like, say, a light bulb that was plugged in, and then there were these cathodes that were sticking in a solution of salt water, the light bulb would be able to run because an electrical current could pass through the bridge of electrolyte solution. A weak electrolyte solution is something that will dissociate in water, but then will recombine. So you don't have quite as many ions. So HF, which is known as a weak acid, and we'll get more into acids a little later, but what we can see is it will dissociate, and then it actually, some of these H and Fs will recombine. A good indicator that it's a weak electrolyte solution, it has this double arrow going back and forth to let you know that you have both the ion and the molecular form. If we were to put a light bulb in there, we would see that there is a weak current. Then we have non-electrolyte solutions. So sugar is an example of a non-electrolyte solution. The sugar is dissolving in the water, but it doesn't break the molecules of sugar up. They still stay little like sugar packet molecules. We just change its phase. So you can see here's sucrose or sugar, and it's in solid form. When we add it to water, it will become aqueous. It dissolves in the solution, but it doesn't break apart into charged particles. The molecules stay as a packet, so it doesn't have an electrical current. So we would say this is a non-electrolyte solution. You could not run any sort of current through this sugar bridge, or the light bulb wouldn't light up. So strong electrolyte solutions, they will conduct electricity. They do dissociate, so they do break apart, and you will have ions. A weak electrolyte solution, you'll have both molecules and ions. It conducts electricity weakly. And then non-electrolyte solutions, you have only the molecules. You don't have any ions, and so you won't conduct electricity. If we look at these, it says complete each reaction for a strong electrolyte solution in water. So when it's a strong electrolyte, it means everything breaks apart. So if I have CaCl2 and it's a solid, and I know that that's a strong electrolyte solution, I want it to break apart. I want to break it apart into its ions. So it'll break apart into C. We're going to have the calcium with a 2+ charge, because calcium always has a 2+ charge. And then we're going to have 2 chlorines. We don't want to keep it as its diatomic chlorine as an ion is not a diatomic. Chlorine as an ion will be just a single Cl. So we want to take that 2 and stick it in front, or say we have 2 charged chlorines. Looking at this one here, this is a little bit different than the first one because we have a polyatomic ion. So in this case, the polyatomic ions will always stay as packets. The polyatomic itself isn't going to break apart into its constituent ions. It itself is sort of an ion. So for this one here, we would go with A. We're going to break apart into 3 potassiums and then this polyatomic ion packet. Again, we don't want to break up our individual components of the polyatomic ion, and potassium is not a triatomic ion. It doesn't exist in that 3 pair. So we would want to pull the 3 out in front as a coefficient. If we were to say, look at this, which of the following reactions represents the dissociation of a strong electrolyte solution in water? So if it's a strong electrolyte solution, it means it's breaking apart into ions to give the electrolytes. So this first one here is definitely not breaking apart into ions. This second one here is just dissolving, right? But it's not actually breaking apart into ions. The molecule is staying whole. This third one here, we do have a molecule, and we can see that we have a single arrow that puts it into its ionic form. So that would be, yeah, we would say that that is definitely a strong electrolyte solution. This one down here, this is like B, in that we're just going from a liquid into a dissolved aqueous form, but it's still staying as a molecule packet, so we don't have any ions to conduct electricity. So just C. Okay, I think we're good there. So we need to talk about what an equivalent is. So an equivalent, which has an equation or a symbol EQ, is the amount of an electrolyte or an ion that provides 1 mole of electrical charge. And that charge could be either plus or minus. So we don't judge based off of the plus or the minus. In solution, the charge of the positive ions will always want to balance out the charge of the negative ions. So if you have 3 positive equivalent, you'd want to have 3 negative equivalent. The concentration of electrolytes in an intravenous fluid are expressed in usually milliequivalents. So if you give like an IV bag, a lot of times they're given as milliequivalents per liter. A milliequivalent, you can think of the equivalent as the base unit. The milli is just a prefix. So 1,000 milliequivalents is equal to 1 equivalent. Just like 1,000 milliliters is equal to 1 liter. So let's look at some examples of this. So if I've got Na with a plus, the ionic charge on this thing is 1 plus. So I would say the number of equivalents in 1 mole is 1 equivalent. You're getting 1 equivalent or 1 charge for every 1 mole. Now, what if we have something that has a bigger charge, like Ca2 plus? This charge is a 2 plus. For 1 mole of this, I'm actually getting more bang for my buck. I'm getting 2 equivalents because the charge is twice the magnitude. If I have iron with a 3 plus charge, in 1 mole of this material, I'm going to get 3 equivalents or 3 bang for my bucks. I get more equivalents the larger the charge is. Let's say we're looking at negative charges. It's the same thing. So chlorine with a -1 charge would have 1 equivalent. Again, notice that if it's a plus or a minus, we don't say that this is like a positive equivalent and this is a negative equivalent. We just call it equivalent based off the magnitude. If we look at, even if we looked at like a polyatomic ion, SO4 2-, we would still just honor whatever its charge is. So it's a 2-, so it has 2 equivalents and you're done. If we look at something like this, let's say we have a solution that contains 25 milliequivalents of Na plus and 4 milliequivalents of K plus. So there's 2 different positive ions. So the total positive charge is 29 milliequivalents. Well, if Cl minus is the only anion or the only thing that's negative, its concentration has to equal the concentration of the positive. So if I've got a total of 29 between these two, then chlorine needs to make up the entire 29 milliequivalents. If there was another negatively charged ion there, let's say like fluoride, we would have to divvy it up between the two. So let's look at this problem here. It says the laboratory test for a patient indicates a blood calcium level of 8.8 milliequivalents per liter. How many moles of calcium are in 0.5 liters of blood? So this is our given piece of information here. We have 0.5 liters of blood. There's a couple different pieces of information. One of them is this thing right here. It says that for every liter, we are going to have 8.8 milliequivalents. Well, we know that we have 0.5 liters of blood. So the first step is to convert from liters of blood into milliequivalents. So I've got 0.5 liters. I multiply it by this conversion factor here. I'm going to put the liter on the bottom and put the milliequivalent on the top so I can get out of liters. So that step will get me into milliequivalents. But I don't want to know milliequivalents because at the end, what do I want to find? I want to find the number of moles of calcium. Well, moles are related to equivalents, right? The number of equivalents is equal to 1 mole. I don't want milliequivalents. So let's get out of milliequivalents, which is the next step. So for every 1,000 milliequivalents, I get 1 equivalent. So at the end of this, we've found that if we have 0.5 liters of blood, I will get 0.0044 equivalents of this calcium 2+. But it says it wants it in moles. We want to figure out how many moles of calcium there are. There is a relationship because looking right here, we know for every 1 mole of calcium, we get 2 equivalents, right? The charge tells us the number of equivalents in 1 mole. So if I know the equivalents and I know that relationship that's built in based off of the charge, we can put 1 mole on top for every 2 equivalents on the bottom. And we end up with 0.0022 moles of Ca2+. So what they're able to do is figure out how many moles of a material there are based off of like the equivalents or the charges that they're picking up. So electrolytes and body fluids, here, you don't need to have these memorized, but here are typical concentrations of electrolytes in your blood plasma. So a majority of the positive cation in your blood plasma is coming from sodium. So, you've got to digest a certain amount of sodium chloride. Then we've got a little bit of trace amounts of potassium, magnesium, and calcium. The total, though, concentration for like healthy blood plasma is 150. So then our anions should also balance that out, right? So as far as our anions are concerned, a good quantity of it is chlorine, right? So a lot of the electrolytes in our blood plasma are coming from sodium chloride, which is what we digest on a regular basis. Then we have some bicarbonate, some proteins. So there's some smaller quantities, but again, both of them equaling 150. So these numbers will vary as a result of your nutrition. Right, if you eat more salt and things like that, sometimes these can be a little bit higher. If you were to get an IV solution, these are some different quantities of the electrolytes that you would find. So let's say you needed like a replacement solution, you would have 140 milliequivalents of this Na plus, 10 milliequivalents of the K plus, so on and so on. What you see is that a lot of these are mostly just sodium, unless you're specifically looking for like a potassium chloride solution. This is for people who have specifically low potassium levels, right? They don't need all the Na, so they're just needing that potassium replacement. So let's, I want you to answer the questions here. In 1 mole of Fe3 plus, there are how many equivalents? In 2.5 moles of SO42 minus, there are how many equivalents? And then this last one here, in an IV bottle that contains NaCl, if the Na plus is 34 milliequivalents, what is the Cl? I'll give you guys 2 minutes for that. Shouldn't take you too long. Okay, so for this first one, if we have 1 mole of this iron, how many equivalents are we going to get? Well, it's got a 3+ charge, so we're going to get 3 equivalents. If this was a 2+, we'd get 2 equivalents. If it was a 1+, we'd get 1 equivalence. In this one, you've got to go a little bit farther. It says, hey, we've got 2.5 moles of a sulfate ion, and sulfate has a charge of 2-. So that means you're getting 2 equivalents in every 1 mole. But we have 2.5 moles. So we need to take our 2 and multiply it by 2.5 for a total of 5 equivalents. The more moles you have, the more equivalents you would expect to get. An IV bottle contains NaCl. If the positive cation is 34 milliequivalents, then the negative anion also needs to be 34 milliequivalents. Okay, those two will balance each other out. So moving into this idea of solubility. Solubility is something's ability to dissolve in a given solution. Here is a person who has gout, usually affecting men over 40. Attacks of gout may occur when the concentration of the uric acid that you have in your blood plasma exceeds the solubility. So happy solubility for uric acid is 7 milligrams in every 100 milliliters. That's how much our blood plasma can hold, 7 milligrams for every 100 milliliters. When you exceed that, it means that it's no longer soluble. That excess stuff can't dissolve in your plasma, so it has to deposit somewhere. So that's why you get uric acid depositing in the joints. So the term solubility, right, is the maximum amount of solute that can dissolve in a specific amount of the solvent. It is temperature sensitive. So depending on if it's a gas or a liquid, we'll talk about that in a little bit, but that can change. Expressed usually as grams of solute in 100 grams of solvent. And it's usually talking about water. For us, for this class, it's going to be talking about water, but there are instances where you can have solubility for other solutions or solvents rather. So how many grams of the solute can dissolve in 100 grams of water? If you are dealing with an unsaturated solution, that means that you're just containing less than the maximum amount. So if the maximum amount of sodium chloride in water is 36 grams in 100 grams of water, unsaturated would be anything less than 36. It'd be 35 grams, it'd be 1 gram, it'd be a half a gram, it'd be no grams. All those things are allowing for there still to be room to dissolve more stuff. A saturated solution contains the maximum amount of the solute that can possibly be dissolved. A lot of times in saturated solutions, you will have both the dissolved and the undissolved version. So here we've got, let's say that this is table salt, NaCl. There is the maximum amount dissolved in solution, and then there is a precipitate at the bottom because it can't hold this. And what you'll find is that some of this is dissolving and some of the dissolved stuff is recrystallizing, getting that happening over and over. So both the ions and the solid are present. Okay, would we classify these as saturated or unsaturated? You take salt and you put it in water and it disappears. We would say that that is an unsaturated solution. Why? Because the salt is disappearing. It's not actually disappearing, but it's dissolving. It means that the solution still has room to dissolve salt. Sugar added to a cup of water does not dissolve, but sits at the bottom of the cup. We would say that that is a saturated solution, right? The water can't hold any more sugar. It has enough sugar in it. So looking at the solubility of KBr, and this is specifically at 40 degrees Celsius, because again, temperature does affect this. So at 40 degrees Celsius, the solubility of KBr is 80 grams of KBr in 100 grams of water. That's pretty high solubility. I mean, it can hold a good amount. Identify the following solutions as either saturated or unsaturated. Okay, so this first one says you have 60 grams of KBr in 100 grams of water. Would we say that that's saturated or unsaturated? Look at what the saturation point is. Saturation is 80 grams in 100 grams. We're only at 60 grams in 100 grams. So we would say that that's an unsaturated solution. There's still 20 grams that this material or this 100 grams can hold. This one's a little bit different. 200 grams of KBr added to 200 grams of water. So we've actually doubled our water sample. So let's go ahead and just divide both of these by 2 to get it to 100 grams. So I'm going to divide this by 2 and divide this by 2. That's the same thing as saying 100 grams of KBr in 100 grams of water. Now we can sort of readily compare it to this. Are we saturated, unsaturated? This is definitely saturated. We're over our saturation point. The last one here, 25 grams of KBr added to 50 grams of water. Again, I'm going to do what I need to get this value here, this 50 grams to 100 grams. So I'm going to multiply this by 2 and multiply this by 2. That's the same thing. The ratio is the same thing as saying 50 grams of KBr in 100 grams of water. I like to convert mine back to whatever the initial one is. So if we're at 50 grams, we are nowhere near our 80 gram mark. We would say that this is unsaturated. We still have room for another 30 grams. Well, 15 grams. If we look at the original sample, we have room for another 15 grams of the salt. So how this temperature affects solubility, of most solids, it increases with increasing temperature. So if I'm dissolving a solid in a liquid, like table salt, its solubility will increase with increasing temperature. That means warm water can hold more salt than cold water. The opposite is true for gases. If I'm dissolving a gas in a liquid, and yes, that does happen. We can dissolve gases in liquid. If you drink fizzy water or, pop or beer or whatever, that is dissolved gas. That's what gives it that effervescent quality. The warmer that something gets, the less gas can be dissolved. Okay, it's the opposite. So warm water holds less gas than cold water. That's why we serve our beer and pop cold, because it keeps the fizz. So here we said, it's got, why could a bottle of carbonated drink possibly burst, explode when it's left in the hot sun? Well, if it's left in the hot sun, what is happening is the liquid that originally was holding the gas can't hold the gas anymore. So the gas has now been released, it's not dissolved, and it goes back to its gaseous form. And when the gas goes back to its gaseous form, it expands and it can burst. Why do fish die in water that is too warm? This is something that happens as sea level sea temperature rises. It's because warm water can't hold the same amount of dissolved oxygen. So warm water will hold less dissolved oxygen. The fish are breathing oxygen. They're just breathing it differently than we are. They're filtering it out through the water. They're not getting the same oxygen quantities, and they die. As far as solubility is concerned, so temperature has an effect on it. Pressure also has an effect on it. So there's this law called Henry's law that states the solubility of a gas in a liquid is related to the pressure above the liquid. So if you have a high pressure sitting above the liquid, you can dissolve more gas. It's like looking at a can of pop that's closed versus a can of pop that's open. In the can of pop where it's closed, this has a pressurized gas sitting above the liquid. So this pressure is what is keeping this gas in solution. As soon as you open the can, you depressurize that headspace, and now the gas that's in the Coke or beer or whatever can now come out of solution. So that's why when you look at like a bottle of Coca-Cola, a clear one, when it's closed, you can't see any bubbles coming out. As soon as you open it, the bubbles start to come out because you've released the pressure sitting above it, and now there's sort of room for this gas to come out of solution. So not all ionic compounds, such as salts, are dissolvable in water. There are certain things that are like always going to dissolve in water. Lithium, if they contain lithium, sodium, and potassium, those things are like always going to dissolve. But there are some things that don't like to dissolve. If you have chlorine and it's combined with silver chloride, that thing is insoluble in water, meaning it'll just sit at the bottom. This is known as a solubility chart or a solubility rule. These are in your textbook. You do not have to have these memorized. I don't expect you to know every single salt combination out there, every metal and non-metal, and if it dissolves in water or not. But you do need to be able to reference them. So when you're doing homework and stuff, you will need to be able to look these up and read what they're saying. So like when looking at this one here, table 9.8, it's saying that these things in general are soluble unless they contain one of these exceptions. There are no exceptions for these first ones. These are always soluble. But chlorine, bromine, and iodine, for the most part, they're soluble unless they're paired with these three. Sulfate is usually soluble unless it's paired with one of these things. Okay, we can go through that. Using the solubility charts. Okay, so we're looking at these different things. Potassium potassium sulfide. This would be soluble because it contains potassium, and potassium is always soluble. Calcium nitrate, this is going to be soluble because it contains nitrate. Nitrate is always soluble. Again, if we go back to this chart, right, if it has potassium, it's always soluble. If it has nitrate, it's always soluble. Looking at this one here, PbCl, this is insoluble because chlorine, when it's combined with lead, forms a insoluble solid. NaOH, anytime you have sodium, it's soluble. Al, aluminum phosphate, AlPl4, contains non-soluble ions. These things are insoluble when they're in water. So you just want to be able to look at this and read it. It says, what ions make each of these compounds insoluble in water and why? Just based off of the solubility charts. I don't want to spend too much time on that. Okay, so how solutions are different than compounds? Well, in a compound, like if I have like table salt, for instance, or let's look at this, Ki. That has a very specific recipe, right? It's 1 potassium for every 1 iodine. You can, no matter where you're getting your potassium iodine, here on the other side of the world, that is the recipe for it. A solution is different because you can actually change the concentrations. You can kind of change its formula, right? So if I have Ki dissolved in water, well, how much Ki do I have? Maybe you put a little more Ki in than your neighbor did, right? So you have to specify how much of this Ki is dissolved in a certain amount of the water or the solvent. That's known as a concentration. A concentration tells you how much solute is in versus the solvent. Over here, they're making a concentration of 5 grams of Ki added to 1 liter of the volume. How do we express concentrations? There's a couple different ways that we can talk about them. So again, the concentration of a solution is going to be expressed as the amount of the solute over the amount of the total solution. The units that we use for amount will shift depending on what type of concentration we're using. So the first one is called a mass percent. We'll go over all of these, but a mass percent is the mass in grams of solute over the mass in grams of the solution. A volume percent, which, you know, no brainer, is the volume of the solute over the volume of the solution. This is kind of a funky one, mass volume percent. This is the mass of the solute over the volume of solution. And then molarity, which is the one we use quite often, that's moles of solute over liters of solution. All right, I will go over all these. Let's do mass percent first. So in the mass percent, we're going to have grams of solute over grams of solution. Now it's important to note that the grams of solution are the solute plus the solvent, right? So it would be the salt plus whatever the water is, the amount of water. You'd want to take into account both of those. If you're given the mass percent, you can write it as grams of solute over 100 grams of solution. So let's say you had a mass percent, it's 13% mass percent. That's the same thing as saying 13 grams of solute, whatever the solute happens to be, over 100 grams of solution. All right, so you've got a quick way to hop back and forth between percent and a conversion factor. So if I've got, when water is added to 8 grams of KCl, it forms a 50 gram KCl solution. The mass percent concentration is 16%. So I would take my 8.00 grams, I would divide it by 50.00 grams. Oh, and I'm sorry, you have to multiply by 100 as well. And then you multiply by 100 and you get 16.0%. So solute, what's getting dissolved, solution, solvent, solute plus solvent. Okay, in this problem, they just gave you the total. So they gave you what the solution was. That's not always the case. Sometimes you have to add those two values. It's a pretty simple calculation. All right, so guide to solving these, state the given and needed, write the concentration, yada, yada, yada. All right, let's do one. So a solution is prepared by mixing 15 grams of Na2CO3 and 235 grams of water. I want you to calculate the mass percent for this thing. Okay, so when working on this problem, you kind of want to note, what is the information? So this here is your solute. That's the thing that's getting dissolved. So that's going to go on the top. This over here is the solvent. So in this problem, they don't give me the information of the solution. So I actually have to come up with the total mass of the solution by taking the 235 and adding it to the 15. So as far as mass percent is concerned, we're going to take our grams of solute over the grams of the solute plus the solvent or the solution for a total of 250 grams, and we multiply it by 100. In this case, we get 6%. So that's one way to calculate concentration, probably the easiest way, one of the easiest ways. We also have volume percent. So this is the percent volume in milliliters of the solute divided by the volume of the entire solution. Again, units for this are in milliliters, you multiply by 100. If I give you the volume percent, like again, if I say, hey, it's 10% volume. You would say that that's 10 milliliters of solute over 100 milliliters of solution. We also have this one, which is mass volume percent, which is kind of a funky unit. It's grams of solute over milliliters of solution times 100. Okay, so if I said, hey, you've got a mass volume percent and it's 35% mass volume, that's the same thing as saying 35 grams of solute over 100 milliliters of solution. Okay, those are the same thing. So each of these things then can be written as a conversion factor. So if I've got a mass percent, specifically 8.5, that's like saying 8.50 grams of NaOH for every 100 grams of solution. I want you to do the conversion factors for these two. Make sure you know what the units are. So this is volume and this is mass volume. Okay, so for this one, the 5.75, it's a volume, so we just want to make sure the units that we're using are matching whatever they're giving. So it's milliliters and milliliters, and you could write it either way. Here I've got 4.8% mass volume. So mass volume, meaning that mass is for the solute, that would be in grams. Volume is for the solution, that is in milliliters. The last one that we have that I think is probably the most used is molarity. And molarity, sometimes people get molarity confused with moles. Molarity and moles are related to each other, but they're not the same thing. Moles is talking about an amount. Molarity is talking about a concentration. So molarity is referencing moles per liter of solution. Moles of solute given over liters of solution. So if I look at something that says, oh, I have a 1 molar NaCl solution, that is the same thing as saying that I have 1 mole of NaCl in every liter of that given solution. What if instead I had a solution that was like 6.0 molar HCl? That's the same thing as saying 6.0 moles of HCl in every 1 liter of solution. Okay. So looking at this one, what is the molarity of a 0.500 liter NaOH solution if it contains 6 grams of NaOH? So what is happening in this problem here? You're given the volume of the solution in liters, so we don't have to do anything with that. But here, we're given 6 grams of the NaOH. Well, molarity equals moles over liters. I have this, I need to get my moles. right? It's not in moles, it's in grams. But moles and grams and moles are like really easy to convert between if we know the molar mass. Can we get the molar mass of NaOH? Oh yeah, we just look it up. So we find here that the molar mass is 40 grams of NaOH for every 1 mole. So we need to convert the grams of NaOH into moles. We've got 6.00 grams of our NaOH. I use the molar mass here to convert into moles, and now I have a mole value of the NaOH. Now with this can then get plugged into that equation, right, of moles over liters. So we have both of our components here. So we take the new calculated mole value, because the gram doesn't work for molarity. So we take our mole value, we divide it by how many liters we have, and we get an ending value of 0.300 molarity. I want you all to do one. So what is the molarity of a 0.225 liter of a KNO3 solution containing 34.8 grams of KNO3? It's very similar to the last problem that we just went over. Okay, so working this problem, it's asking about molarity. So I always just kind of write my equation out. Molarity equals moles over liters. I know liters already. It's this thing right here. I need to get moles. So I have to calculate moles from a gram value. So we need the molar mass of our KNO3, which is 101.11 grams in every 1 mole. We then take the 34.8 grams and just convert it into moles. Now that we have the mole value, we can drop that into our equation, divide it by our liters, and we should get 1.53 molarity KNO3. Your units for molarity can be used as a conversion factor, meaning that when you're solving for a different thing in the equation, I did not have my coffee this morning. When you're solving for a different thing in the equation, like let's say you're not solving for molarity, but you're trying to solve for moles or you're trying to solve for liters, you can use this conversion factor. So 3.5 molarity HCl is the same thing as saying 1 liter is equivalent to 3.5 moles of the HCl, right? Or these are both appropriate conversion factors. So let's say we have a problem here. It says, this isn't talking about molarity, but we're going to use a conversion factor anyway. We're talking about mass. It says how many grams of the NaOH are needed to prepare 75 grams of the solution. So we want to figure out grams of the solute, right? We have grams of solution. And we also have our mass percent. So I'm going to change this into a conversion factor. 14% is the same thing as saying 14 grams of the solute, which is NaOH, in every 100 grams of the solution. Right? Mass, gram. Now I can go from my given information, which says I have 75.0 grams of the solution, and I can just actually multiply it by the conversion factor in this setup. I will get 14 grams of NaOH in every 100 grams of the solution. The grams of the solution will fall away and we'll just be left with grams of the NaOH. So we take our original, multiply it by 14 and divide it by 100. We get 10.5 grams of NaOH. I want you to do the same thing for this one. This is slightly different only in that it's in a volume. Okay, so you're going to be using milliliters instead of grams. But I want you to take the percentage that's given, write it as a conversion factor, and then prepare your solution. Okay, so again, the key thing here, being able to take this and write it as a conversion factor. So if it's 5.57%, that's like saying that I have 5.75 milliliters of ethanol in a 100 milliliters of solution. We have an amount of ethanol. We want to figure out the solution. So I've got 2.25 milliliters of ethanol. So that means I need to flip-flop this, right? I want to calculate solution. So 100 milliliters of solution for every 5.75 milliliters of ethanol. The ethanol will fall away and we'll be able to just keep our milliliters of solution. So wait, hold on one second. How many milliliters of a 5.75 milliliter can be made? Yes, okay, yeah, correct. Oh, hold on. So we take the 2.25, we multiply it by 100 and then divide it by the 5.75 and we get 39.1 milliliters of solution. Let's see, there's so many of these. We'll do this last one, okay? So this one here, how many grams of AlCl3 are needed to prepare 125 milliliters of a 0.150 molar solution, molarity solution. So I want you to solve this one. This one is talking about molarity. So first get your molarity into a conversion factor and then look at what's given and try and figure out where you're headed from there. And we'll give you all for that one. We'll give you 3 minutes on that one because this one's requires a couple additional steps. All right, so here we've got molarity. And I'm going to write my molarity as a conversion factor. So it's 0.150 molarity, which means I have 0.150 moles of AlCl3 in every 1 liter of solution. That's just what molarity is, right? It's moles per liter. So I'm given a value of milliliters and I want to know something about grams. This is a couple steps. I've got to go from milliliters to liters. From liters, then I can get into moles. And then from moles, I can get into grams. So I'm going to start with the 125 milliliters of the solution. I'm going to convert that into liters because this is a relationship of liter to mole, not milliliter to mole. So, so for every 1 liter, I get 1,000 milliliters. Then from there, I can use this relationship that says, well, I get 0.150 moles of AlCl3 in every 1 liter, right? The milliliters will cancel, the liters will cancel. And then the last step is to calculate grams. So 1 mole of AlCl3, I have no idea, it's whatever its molar mass is. Okay, so hopefully you calculated that. So moles will cancel. Multi-step, so 133.33 grams. So we had to do a couple things. So first we had to get it into liters, then we go into moles, then we can get into grams, or 2.5 grams of AlCl3. So you want to be able to manipulate those concentrations to calculate any of them. Now, if you were like, well, I don't really like that idea of using it as a conversion factor, I just want to go molarity equals moles over liter and be like, you know, well, if I know this and I know this, can I just isolate and solve for this? You can totally do it that way as well, okay? If that feels more comfortable for you, you do a lot of math and you just like plugging it into an equation, I'm fine with that. It will give you the same answer as making it a conversion factor and running it through dimensional analysis. Okay, so you do whatever works for you. All right, we're gonna stop there. Yeah, because we'll do solution dilution next time. Yeah, and that's all I've got for today. So let me know if you guys have any questions. Otherwise, I'll see you on Thursday. Enjoy the rest of your day. Bye, guys.